Hello everyone. Thank you for participating in my presentation. My name is Seunghwan and I'm going to talk about a new continuous subgraph matching algorithm. First, we will give the definition of the problem and we will talk about the previous work and introduce our algorithm called Symbe. Finally, we will show the experimental results and conclude this talk. For simplicity, we focus on undirected, connected, and vertex-labeled graphs. However, we can easily extend our techniques to directed or disconnected graphs. For given two graphs Q and G, an embedding of Q in G is an injective mapping from Q to G such that the map vertex have the same label and the corresponding edge exist. So the subgraph of G shown in blue is one of the examples of embedding of Q. As you can see, this blue subgraph is identical to Q. A homomorphism is similar to an embedding. The difference is that the mapping does not have to be injective. So it is okay if two vertices U1 and U5 are mapped to one vertex V1. Therefore, this subgraph is also homomorphism. This problem deals with dynamic graphs that change over time through graph update stream of edge insertions and deletions. This figure shows the dynamic graph with two edge insertion, delta O1 and delta O2. For given choreograph Q and dynamic data graph G, the continuous subgraph matching problem is to find the positive or negative matches for each update operation. Here, positive matches mean the new matching results and negative matches mean matches that are deleted. When delta O1 is inserted, there are no positive matches, and when delta O2 is inserted, there are positive matches of Q. The blue subgraph is one example of a new match. In order to solve this problem, the state-of-the-art algorithm called FLOS stores the information of partial matches of spanning tree from choreograph. Since TOFLOGS use the spanning tree, it does not consider the non-tree edges for filtering. Therefore, when delta O1 is inserted, TOFLOGS should perform subgraph matching to find matches because there exists a match of spanning tree in data graph. Also, due to a symmetric update process of data structure, processing edge deletion is much slower than edge insertions in TOFLOGS. This is an overview of our algorithm. Given choreograph Q, first we build a looted DAG from Q instead of a spanning tree. Next, we'll build an initial auxiliary data structure called DCS from DAG and initial data graph. This structure stores weak embeddings of DAG in G. Next, for each update operation, we update the data graph and the DCS structure. Based on the DCS structure, we find matches by calling the backtracking procedure. The path tree of a looted DAG is the tree such that each root-to-leaf path corresponds to a distinct root-to-path in DAG. Also, this tree shares common prefix of paths. Now we can define weak embedding of the DAG. A weak embedding of DAG is defined as the path tree as homomorphism of the path tree of the DAG. The subgraph in G indicated by the blue line is an example of the weak embedding of the sub-DAG of Q with U3 as root. The point that I would like to focus on is that the weak embedding is a necessary condition for an embedding. Therefore, we can use weak embeddings for filtering. Our data structure, DCS, stores the information of weak embeddings in D1 and D2 arrays. D1 stores the existence of weak embeddings of the reverse curry DAG. D2 stores the existence of weak embedding of curry DAG with D1 value of 1. So D1 into V3 is 1 because there exists the weak embedding of reverse stack with U2 as root in V3. We can compute D1 and D2 by dynamic programming. So we need to update the structure for each update operation. When delta O2 is inserted, you can see that the multiple edges can be inserted into DCS at once. Also, to update D1 and D2, recomputing the entire process of dynamic programming is obviously inefficient. Therefore, to update D1, we start at the endpoint of the update edge and update D1 downwards until D1 does not change. For example, for the blue line, we first update D1 input with 6 from 0 to 1 and iterate recursively for the children below it. Also, we can update D2 similar to D1. The difference is that the update can start even even on vertices where D1 changed. So how can we use this information to find matches? As we saw earlier, since a weak embedding is the necessary condition for an embedding, we only need to consider weak pairs with D2 value of 1. For example, the endpoints of this red line has D2 value of 0, so we can see that there are no positive matches without backtracking. For the blue line, since D2 are 1, we start backtracking with a partial embedding containing this blue edge to find positive matches. For performance evaluation, we compared our algorithm SymB with TopFlux. We use two datasets, that is bench and NetFlow. For these datasets, we generate a set of 100 queries for size 10 to 25. Also, we use the queries using the TopFlux. For each query, we set a 2 hours time limit and measure the average elapsed time and the number of solved query graphs within the time limit. For sensitivity analysis, we vary the insertion rate, deletion rate, and the dataset size. This shows the results of varying the query size. SymB is displayed in black box, and as we can see, that our algorithm is up to 1,000 times faster than TopFlux on NetFlow, and up to 30 times faster than TopFlux on Alice Bench. The reason for the lesser performance gap is that Alice Bench has 45 edge labels, and thus it is an easier data set to solve than NetFlow. This figure shows the results of varying the insertion rate. As we can see, that our algorithm is outperforms TopFlux. For varying the deletion rate, the performance gap for varying the deletion rate, our algorithm also outperforms TopFlux. However, the performance gap between two algorithms decreases as the deletion rate increases. This is due to the queries that TopFlux cannot solve, but SymB solves within the time limit. As we can see in the figure below, the elapsed time of the TopFlux with many queries has already reached the time limit. So even if the deletion rate increases, the elapsed time of TopFlux no longer increases, but the elapsed time of our algorithm increases. So when we measure the average elapsed time with queries that TopFlux solves within the time limit, the performance ratio between two algorithms increased from about 200 times to about 300 times as the deletion rate increases. This shows that our algorithm handles the edge deletion case better than TopFlux. To summarize, we proposed a much faster algorithm for continuous subgraph matching based on the DAG of the query graph. And please refer to our paper for other experimental results. Thank you.